Hi everyone, this is Wei Zhao, and here is my ISP video about the relationship between area and population in Asian countries. In this video, I'm going to discuss about how I gather my data and what I found after my research and analysis. So let's get started. First of all, I want to discuss about what my topic is, how I gather my data, and why I use this topic as my research topic. So my topic again is about Asian countries' area and population relationship. The reason why I chose this topic is this. So as we know, the population of the country can be affected by several factors, such as temperature, GDP, economy, climate, and so on. Well, area, our main character, the size of the country is one of the most important factors, yet sometimes it doesn't seem to affect the population very much. So for example, Australia is the sixth largest country in the world, yet its population is only the 53rd biggest. Therefore, I like to research about this topic to analyze if there's really a strong connection between these two variables. To do so, I want to analyze 50 plus pieces of data from 48 Asian countries. And the reason why I chose Asian countries is because they have really close social values, environment, and culture, so that the data I'm going to collect will show direct relationship between area and population. So about my hypothesis, I believe that the population should increase when area increase, and the population should decrease when area decreases. I feel that there should be a really strong relationship between population and area. So about how I collect my data, I actually find secondary data from the internet, and there's no bias and issue because the data I collected, they're all updated in 2017 and they're the latest data, and I checked them 3 times to make sure they're not wrong. So there's really no bias and issues, and later my analysis can also prove that my data collecting method is right. So here are all my raw data. Here is the green bar, which is listed with the country's name from in alphabetical order from A to Y, which are all Asian countries, and the purple bar is my area value, and the yellow bar is my population value. As far as we can see, my raw data are pretty random. For example, this area value has a very small value, while this one is pretty big. This population value is relatively small, while this one is relatively big. So I believe that with these random collected data, after my analysis, I can show that my hypothesis is either right or wrong. So let's talk about my independent data and my dependent data. In this case, because I use area as X value and population as Y value, since area actually affects and changes population, so area should be the independent one and population should be the dependent variable. So let's talk about measures of central tendency first. Measures of central tendency is a way to present the majority of a dataset by using a specific data value. We have 3 methods in total. The first one is mean, which is the sum of all values divided by the total number of the values. Then we have median, which is the middle value when the data is ranged from the smallest to the largest. Last, we have mode, which is the most common value, the value that appears most frequently in the whole data set. So in this case, mean is actually the best way to represent the majority of the data because usually used in continuous data, mean actually minimizes the error of using it to show other value in the dataset better than the 2 other methods. Besides, median in my dataset is actually not really useful and practical because my data values are not evenly distributed. So the mean won't be in the center of all of the data values, and not all the data values will be very close to it. Well, in addition, mode in this case, I got no mode as we can see in both values. This is because, well, there's really no equal area or population among Asian countries or any countries in this world because every country is different and there won't be an equal value, so mode is not useful is not available in this occasion. So let's talk about histograms. Histograms are charts that represents the distribution of data. In this case, just as what I referred before when we talk about measures of central tendency, my histogram is not really evenly distributed. So as we can see, both of my histograms, they are positively skewed because the value starts from here, goes to top, and then it drops and becomes more and more close to 0. As far as we can see, most of the values in these two charts, they gather on the left side, while there are only a few big values on the right side, and there's just a few of them. So in this case, the histograms is not really even distributed, which illustrate that most of the countries, they have a really close value to each other in area and population, while some countries, they have really huge area or really huge population. So that which gives us these kinds of graphs. So now our next topic is about the variance and standard deviation of area and population. By using the equation of variance and standard deviation, we are able to calculate these two values. Variance is the average square difference of values from mean, and standard deviation, which is the root of variance, is actually the average difference of values from mean. The number of these two values, they actually represent if the data are far away or close from the mean, which also means that if they are far away from each other, if the values are far away from each other or close to each other, in this case, apparently my standard deviation, as we can see, and my variance, they are extremely huge, which should be indicated that both of the two variables, area and population, they all have values that are pretty much spread out and really far away from mean. However, it might not be true because the variables I use, area and population, they have really huge values. So because the value of the variables are large, it might make the variance and standard deviation larger than it should be. So we cannot really indicate whether the data values are spread out or far away from mean or not. So let's talk about quartiles. There are 5 important numbers in the whole data set, which is maximum, the biggest value of the whole data set, and minimum, the smallest value. We also have Q1, Q2, Q3, which are 3 points that divide the whole data set into 4 equal groups. That is to say, minimum to Q1 equals to Q1 to Q2 equals to Q2 to Q3 equals to Q3 to maximum equals to 25% of the whole value, a whole data set. There's also interquartile range, which is equals to Q3 minus Q1. So here are my quartiles of area and my quartiles of population, and we are going to use them to make the box and whisker plot so that we can really understand what is the area in our data value in our data set. Are they close to each other or are they far away from each other? So here are my box and whisker plot. Box and whisker are actually graphs that represent the distribution of data, which are more persuadable than variance and standard deviation. In this case, as we can see, my graph, they looks pretty short than normal ones. Usually your graph should be something like this, like that long, while mine is only that short. This means that my values are really close to each other, actually, in fact, especially in this part from minimum to Q2. And the same goes with my population graph, which is from minimum to Q2. They're actually the closest value. Well, from this here, from Q2 to maximum, they are actually a little bit more spread out, but still pretty close to each other. This indicates that most countries' population value and area value are very close to each other in some sort. So let's talk about my two variable data analysis. Here we are going to put my independent variable and my dependent variable together so that we can learn about the real relationship between them. So let's start. So here I put log regression equations and R value and R square all together to illustrate my whole analysis about the connection between these two variables. So the line of best fit, which is this line here in my two variable scatter plot graph, it is a straight line that best describes the trend in the scatter plot. Its equation is actually log regression equations. As we can see, here's this regression, and it's actually the same as the log equation. And its coordinates is actually the log value, which is its m value and b value. If we see the whole equation as y equals to mx plus b, so m 44, m b 484968411, and same value here. So the line of the best fit, it actually shows linear correlations, which is the relationship in which a change of a variable tends to correspond to a proportional change into another variable. In this scatter plot graph, about the relationship between the two variables, the line of best fit is actually increasing, as we can see, and the data, most of them are pretty close to it. This is because our R value. So our R value that we figure out is actually 0.45. In this case, so if you guys remember about the strength and the weakness of R value and data, the distance of data, the scale is like this. So from 0 to 0.33 is the weak relationship. From 0.33 to 0.67 is the moderate relationship. From 0.67 to 1 is the strong relationship. In this case, 0.45 is actually in the middle between 0.33 and 0.67. So therefore, it proves that the relationship between area and population is actually positively moderate. Besides, the line of the best fit should actually be a solid line in my graph because the data I have been researched on are continuous data. According to my line of best fit, it's actually positive. So the population is actually increases when area increases, and it decreases when area decreases. Let's talk about my residual plot. A residual is the difference between y value and the expected value. By subbing x value into the line of best fit, we can get the expected value of the y variable. Then by subtracting the actual y value, which is the raw data I have, with the expected value, we can get the difference, and the difference is actually the residual. A right residual plot should have some scattered point like this, randomly scattered in the graph with no patterns like mine. So basically these points, they're randomly scattered and there's no pattern or anything. So which means that we do have a line of best fit and our data collecting method is correct. All of the data collection we made are totally right. So here are my conclusions. It is correct for my hypothesis that population does increase when area increase and does decrease when area decrease. However, my hypothesis does get some part wrong. So there's really no strong relationship between these two variables. Instead, the relationship is actually moderate, according to our line of best fit graph. Besides, most of my data, they are relatively small, while few of them are relatively large. There's also this really interesting discussion in my data about if the data is close or far away, and our box and whisker plot actually prove that our data are relatively close to each other. I'm very satisfied with my conclusion and with the result I get, and my hypothesis is mostly right. However, if I can do my ISP next time, I will considering using variables with smaller numbers because they are much easier to calculate and it is much harder to make mistakes. So, this is the end. Thank you for watching.